Hey guys, so tonight we're going to talk about some discrete mathematics. So first I want to talk about a factorial, and that's the product of the number and all the positive integers less than the number. It's usually wrote using an exclamation point. So an example like I have below here is like 4 factorial. It's 4 times 3 times 2 times 1, in which 4 factorial ends up being 24. The next is 3 factorial. That ends up being 6 because it's 3 times 2 times 1. The next one I have for you is 2 factorial. 2 times 1, so just 2. The next one is 1 factorial. And the only way that makes sense for me to explain this is just that if you have 1, 2 over 2 is 1. So when I use 2, I'm assuming you could use 3 also. But you would have to do 3 factorial and so forth. But here I have 2 factorial over 2. So 2 times 1 is 2 over 2 is 1. The next I have is 0 factorial. So I use the next one up. So 1 over 1. 1 factorial over 1. Well, 1 times 1 is 1 over 1 is 1. Alright, so next is permutations and combinations. So a permutation is the ordered sequences of elements from the given set of data. The permutations order is very, very important. So the number of permutations can be seen in your calculators in PR. The formula for it is n factorial over n minus r factorial. You can also do this in the calculator, which we will cover later. And so next is a combination, and a combination is the sequences of a unique combination of elements from the given set of data, and order does not matter in this one. And a number of combinations for a group is NCR, which is the same as the previous formula, only adding r factorial in the denominator. You can also do this one in this calculator, and we'll learn how later. So some examples of finding permutations and such would be, for such permutation, we find the number of permutations when 2 of the 3 elements are used, where n is 3 and r is 2. So here they're telling you exactly what n is and exactly what r is. That's not always the case. A lot of times it'll be a word problem telling you that you need to fill 4 positions on a board and no one can have the same position and so forth. But this one's a really easy one that they tell you what to use. So we're doing 3 permutes 2. So 3 factorial is 3 times 2 times 1, which is equal to 6, over 3 minus 2, which is 1. 1 factorial was 1. So 6 over 1 is equal to 6. So this set has 6 permutations. The next one is combination. So we do the same as permutation, just add r to the denominator, r factorial to the denominator. So if we're using the same example from before, using 3 and 2 for n and r, then we're doing 3 choose 2. Often we have combination we want to choose. So we have 3 factorial over 2 factorial times 3 minus 2 factorial. And as you can see, it's kind of hid here behind me, but 3 factorial is equal to 6, and 2 factorial times 3 minus 2 factorial is 2, so 6 over 2 is equal to 3. So it has 3 combinations. The next thing we want to talk about is disjunctions and conjunctions. So this is often known as and or intersects in union. So a disjunction is also known as or that's like a V, and it is also known as intersects depending on how you're reading it. So some examples would be A or B, which is read as A or B, or A intersects B. And as you can see from this Venn diagram, if we have A or B, that means we want everything that's in A or everything that's in B. So together all circles are shaded. So in conjunction, we write it as like an upside down V. That can be read as and or union with something. So some examples would be A and B, or A union with B. And as you can see from the Venn diagram, that if we want A and B, it's only the middle section that is both A and B. So next I want to show you some truth tables. And so here we're going to read this as, we'll read that as phi x, and then for the first truth table we're talking about or, and the second one we're talking about and. So I just wanted to pull these up and show you because this should be something that you know for sure for the praxis, because they'll often come up on the praxis quite a bit. So it's very important to know that in an or situation or intersex situation, that as long as there is true somewhere in it, it's going to be true. It doesn't matter if the true comes in the phi or the true comes in the x. If true is in the equation, then it's going to be true. But if it's two falses, then obviously it's going to be false, because false or false is going to be false. So then we move on to the and for an and to be true, the only time it's true is when both are true. If there is a false in an and statement at all, it is automatically false. So here's a couple more to show you. Sorry that my arrow got messed up there on the very first one. But we're talking about phi and x again, and the first table is an if-then statement, and the second table is an if and only if. There should be an arrow pointing from the phi to the x in the last box there. So for the if-then statement, which is the first table here, I just wanted to show that the only time that it can be true, the only time it can be false is if a false follows the true. So now that sounds confusing, but basically just remember that anytime you see an if-then statement, it is true, unless the statement is true and then false. True if then false, the statement is false. True if then true, it's going to be true. All of it's true unless it's true if then false. So the next table is if and only ifs. So these are basically, if there's a true and a false in it, it's going to be false, because true if and only false makes no sense, and false if and only true is going to be false. So the only time it's true is if you have both trues or both falses. And the falses kind of act like negatives, because two negatives make a positive. So just remember that two falses make a true in an if and only if statement. So the final thing I want to go over is just a Morgan's theorem. It shows up some on the praxis. It's a very basic theorem. It's just basically showing that if you're negating a statement, then the negation goes to every single element of the statement. So for instance, in this first situation, we are negating A or B. So that means we distribute that negative to the A, or not negative, but the negation to the A. We distribute that negation to the B, but we also distribute the negation to the or symbol. And if there's an or, so if there's an or pointing up like this, and we're like negating it, then we flip it, and it becomes and. So the opposite for the other one, if we're negating A and B, the negation goes to the A, and the negation goes to the B, and it also goes to the and. So if we have and we negate it, that means it gets switched to or. So it becomes negation of A or negation of B. And that's all for tonight. Thank you.